Hello, I'm Ben Wilson of Machlett Laboratories in Stamford, Connecticut. We're here to discuss the Dynalyzer 3 X-ray calibration system. But first, an introduction to Machlett. We've been in the X-ray components business for something over 50 years. We offer 8 product lines consisting of X-ray tubes for CT application, collimators, image intensifier tubes, image intensifier systems, test equipment, automatic film processors, and digital imaging equipment. Let us review the history of the development of Dynalyzer. Please refer to slide number 1. In 1973, the Dynalyzer 1 was introduced. It had the capability of measuring anode KVP, cathode KVP, filament current, MAS, MA, time, and weighed approximately 50 pounds. In 1976, the Dynalyzer 2 was introduced. It had the capability of measuring anode KVP, cathode KVP, MAS, MA, time, line voltage drop, standby filament current, boost filament current, and MR. It consisted of 4 boxes. We displayed the data digitally, and we had a hard copy printout capability. The weight was 66.5 pounds. On the next slide, we'll look at the parameters that can be measured by the Dynalyzer 3 system. In 1982, Machlett introduced the 3rd generation of the Dynalyzer. This had many of the capabilities of the Dynalyzer 2 in that it could measure anode KVP, cathode KVP, MAS, MA, time, line voltage drop, standby filament current, and boosted filament current. The Dynalyzer 3 added the following capabilities: anode plus cathode KVP, MR per MAS, MR per second, coefficient of variation of 10 values, sliding sampling window for falling load generators, storage and recall of 10 exposures, printout of kiloheat units per exposure, printout of line voltage regulation, digital display of data, digital printout of data with a weight of approximately 55 pounds. The Dynalyzer 3 system consists of 3 units: the high voltage unit, which is sometimes called the bleeder, the digital display with integral printer, and the radiation probe. Let's look at the specification on the Dynalyzer 3 system on the next slide. The Dynalyzer 3 specifications are as follows: KVP, 20 to 150 KVP, plus or minus 1%. Rad MA, 10 to 2000 MA, plus or minus 1%. Fluoro MA, 0.1 to 50 MA, plus or minus 1%. MAS, 0.1 to 9999 MAS, plus or minus 1%. Time, 1 to 9999 milliseconds, plus or minus 1%. MR, 0.1 to 6550 MR, plus or minus 0.1 MR. Filament amps, 0 to 20 amps, plus or minus 1%. Line voltage, 0 to 600 volts AC, plus or minus 1%. Input power required, 104 to 125 volts AC at 60 hertz, 76 watts. Or 208 volts to 240 volts AC at 50 hertz at 76 watts. There are 3 units with a total weight of approximately 58 pounds. This is the Dynalyzer 3 high voltage unit, or sometimes called the bleeder. It has 5 coaxial connectors on the front. The first connector is for reading anode to ground on the scope. The second one, cathode to ground. We can read filament current. We can also read MA. An addition that we've made on Dynalyzer 3 over the Dynalyzer 2 unit is a coaxial connector to look at the summed KV. We also have a connector here where we take a 20-foot jumper cable from this unit to the back of the digital display and take that in the booth with us. We have a pressure gauge which indicates the pressure of SF6 gas which we have inside the unit. The other addition that we've added to Dynalyzer 3 over Dynalyzer 2 was the capability of changing the sensitivity of reading MA. Please refer to the next slide. There were 2 changes put into Dynalyzer 3 high voltage unit over that of the Dynalyzer 2. The first is the dual MA range. The second is the anode plus cathode scope output. On the dual MA range, you'll note the switch on the front of the Dynalyzer 3 high voltage unit. In one position, it's fluoro. We're able to read from 0 to 50 MA, primarily for the fluoroscopic readings, and in the rad position from 10 to 2000 MA. We'd now like to discuss the Dynalyzer 3 display, the way we use it at Machlett. But first, we'd like to advise that many of the new features installed in Dynalyzer 3 were done so to help you do the compliance testing as required by the US BRH regulation. We also provide with the Dynalyzer a 20-foot jumper cable that will allow you to pick up input line voltage to the generator. This connector connects into the rear of the Dynalyzer. The other ends are not terminated to allow you to terminate them in a manner that's most convenient for you for picking up the input voltage to the generator. We also recommend that you use an extension cord that's very similar to this, where you can go into 115 or 230 volts. We can use this part of the extension cord to hook the Dynalyzer into it, so we will eliminate any possibility of ground loops. Now let's look at the way the Dynalyzer hooks into the circuit. Please refer to the next slide. This is the way we connect the Dynalyzer in the circuit. The Dynalyzer high voltage unit or bleeder is mounted on the X-ray table and is connected between the X-ray transformer and the X-ray tube. We connect the 20-foot jumper cable from the front of the high voltage unit to the back of the digital display and take that in the booth with us. We also connect the radiation probe to the back of the digital display and mount it on the X-ray table in the beam. Note the conformance test stand position, and we'll hear more about that later. There is an optional Dynalyzer 3 printer, standalone printer that can be built for those units purchased without the integral printer. Now that we have the Dynalyzer hooked into the circuit, we're ready to use it as we do at Machlett. We turn the power on here. First thing we look at is line no load, or line input voltage. We then switch to filament amperes and read standby filament amperes. We squeeze the trigger on the X-ray generator and read boosted filament amperes. We're now ready for our first shot. We have a simulator with us that will allow us to input the signals to the Dynalyzer very similar to those that we would get from an X-ray generator. On the top LED, we'll be reading summed kV, or anode plus cathode. Recall that we measure kVp to 1% accuracy, and the high voltage unit is frequency compensated to 100 kilohertz, which allows us to see spikes and transients that are not normally seen on other equipments of this type. On the next LED, we measure MAS, we divide by time, and have MA available to us, both of which are stored. On the next LED, we'll be measuring time in milliseconds, and we'll hear more about that in a few minutes. On the next LED, we're measuring MR, or radiation, assuming we have the radiation probe in the X-ray beam. Remember, this is a microprocessor device. Since we have the data available to us, we can then calculate MR per second and MR per MAS. All of these can be printed out on hard copy on this unit. On the last display, you're going to read line voltage drop. We also print out the percentage of line voltage regulation, since that is a BRH requirement during compliance testing. We're now ready to go to the next slide to see the data that's been made available to us on the first exposure. Data obtained on the first exposure is peak kV, MAS, MA, time, MR, MR per second, MR per MAS, standby filament current, boost filament current, no load line voltage, loaded line voltage, and we print out percentage line regulation and kiloheat units per exposure. We now move to the central panel of the digital Dynalyzer. We have three controls that are interrelated: the trigger source, the trigger level control, and the trigger mode switch. In the trigger source, we have 5 positions, or 5 different ways that we can trigger the digital clock in the Dynalyzer. The first one is KVP, which will be used by most of the people. We also can trigger from MA, assuming it's a constant potential equipment, or we can trigger from the external trigger in a laboratory setting. In this case, you would insert the triggering signal into the coaxial connector on the back of the digital display. On the Dynalyzer 3, we added 2 additional positions. One was the auto mode. Let's assume that we have the Dynalyzer in the circuit during a fluoro run. When we step on the foot switch, we trigger this unit and we take our readings. And that would be the case. That would only be the case if we did not have the auto mode. In this mode, we're going to trigger the unit every second, such that When we press the foot switch, the unit is being triggered every second. The automatic brightness stabilizer takes over and moves kV or MA. While we're triggering every second, we will constantly have our numbers brought up to date. It's also very useful in the calibration in that filament, in that you can constantly trigger this unit in the auto mode once per second and adjust your filament current. The other position of the switch is MR. In this case, we plug this unit into the wall socket, put the radiation probe into the X-ray beam, take our shot, and we will then read MR and time. It is not necessary to have the high voltage unit in the circuit during that particular mode. The next control is the trigger level. This establishes the level on the pulse where we're going to trigger the digital clock or we're going to measure time. In the single phase mode, we would prefer to do it at the 10% level, in that we would get just above the level of grass. In three-phase, it's an entirely different situation. It is our understanding that most American manufacturers, General Electric, Picker, Raytheon, Zonix, will trigger off the 75% level. What we would do is then dial in 75% into the trigger level control, take our shot, and assume we had 100 kV set into the generator. We would then trigger our digital clock at the 75 kV level. If we're in European equipment, we understand Siemens and Philips trigger or measure time at the 70% level. At this point, we would dial back to 70% and use that level. Regardless, we recommend that you consult the manufacturer's manual to determine where they measure time and measure that in the same manner. The next control is the trigger mode switch. It has two positions, the percent, which is sometimes called automatic, or preset, which is sometimes called manual. In a percent mode, recall we had an American General Electric X-ray equipment. We are going to measure time at the 75% level. This position of the switch allows us to retain the 75% level as we move the kV setting on the generator up. Remember, we had 100 kV, 75% of that was the 75 kV level. If we adjust the generator voltage up to 120 kV, this will automatically calculate 75% of the new value and set it then the threshold at the 80 kV level. In the other position of the switch, preset, or commonly called manual, we are going to dial in the absolute value of the signal that we're triggering from. Thus, we do not calculate automatically. We have to do it manually. Triggering, let's use those same values again. 100 kV set into the generator. It's a GE equipment, three-phase. We would then dial in 75 kV. If we move the input generator voltage up to 120 kV, we would then have to calculate ourselves and dial in 75% of that value, or 80 kV here. One cautionary note, in a percent mode, when we move the voltage back down, we cannot trigger the unit. It is necessary, as you come back down in voltage, to push the reset, clear the memory, take two more shots. One to sense the kV in the generator, and the second to set the reference level. This is a common problem in usage of this equipment in the field. We now move to the kV delay control, which is used to delay at what point on the pulse we're going to measure the kV. The kV control will delay from 0 to 20 milliseconds. Let's now look at the slide to get an illustration of that. Most three-phase generators have a leading-edge overshoot, as shown on this slide. The kV delay control can delay the point of measurement out 20 milliseconds to determine if that is in fact the case. You'll note that we have the 100 kV set into the generator. We very likely would be getting 105 kV read on the display. We then turn the knob out to 20 milliseconds, and we can have a look that far out and note that it's 100 kV and understand what our problem is. The next control is the window delay. The purpose of this control is to better calibrate falling load generators. When we crack the knob, we establish a 20 millisecond sampling window that is adjustable from 25 to 1,000 milliseconds in this fashion. You'll note the 1,000 milliseconds on the display. Let's now look at the next slide to see how it works. This slide shows an illustration of the new window feature. Note we have the plot of a Phillips 3-step falling load generator with MA on the left and time. We'll note the 20 millisecond sampling window in the second step of the waveform. We can delay this 20 millisecond window from 0 to 1,000 milliseconds, thereby looking at each step very closely. We can also use this feature to look at the MA stabilizer operation, as noted on the waveform on the bottom. The next control is the procedure control. It has 3 positions. The first position is coefficient of variation. The second position is normal. The third position is system test. Now let's go to the next slide to see what the requirements are for coefficient of variation of radiation measurements. One of the requirements in the BRH regulations in compliance testing is coefficient of variation of radiation measurements. Coefficient of variation of radiation shall be no greater than 0.05 over a series of 10 consecutive measurements taken within a time period of 1 hour. We also note that all variable controls for technique factors shall be adjusted to alternate settings and reset to the test setting after each measurement. The standard deviation formula shown here should then be used to calculate the deviation. We do that a little differently on the Dynalyzer, which you will see shortly. The Dynalyzer 3 memory has a capability of holding 10 exposures. That's the data that's necessary to do the coefficient of variation that we saw in the previous slide. We have an exposure counter in the Dynalyzer that will tell us the number of exposures that we have in memory at any point in time. We will now insert 10 exposures in memory with our simulator. We now have 10 exposures in the memory. In order to do the coefficient of variation calculation, we switch the procedure switch to the coefficient of variation position. At this point, on the 4th LED, or the radiation display, we will be able to read the calculation of coefficient of variation of radiation as required by the BRH. If we have a problem there, that problem is no doubt derived from one of the other 3 parameters, time, MA, and KV. Thus, we have done a coefficient of variation calculation on that data also. The coefficient of variation can be printed out so that we would have a hard copy as proof of having done the coefficient of variation calculation. We have another feature in the Dynalyzer that we consider quite excellent. We're able to recall any of the 10 exposures that we have in memory back to have a look at them for further analysis. We're to depress the button. We would bring back exposure number 9, press it again, exposure number 8, and so on, down through 1, and then back to 10 again, and we can continue around the loop. Excellent feature to be used for troubleshooting. Most microprocessor devices that we're aware of have a self-test capability built in. We have done that with the Dynalyzer 3. The third position on this procedure switch is the system's test position. When we switch this down here, we run a program through the microprocessor to test its functions. If it is not operating properly, the error light on the front of the panel will be illuminated. We will also see in the trigger level display a 3-digit number. That can be identified by the plaque on the back of the Dynalyzer as to the problem with the unit. The other thing we can do is look at the 10-volt power supply when we switch the anode switch up to anode, the KV switch to anode. We'll now move to the third panel of the Dynalyzer 3, where we have 3 buttons and a switch that we will be concerned about. The first button is the manual trigger button, which allows us to trigger the unit manually. The second button is the clear reading button, which clears out the front of the display, very similar to your hand calculator. The third button is the reset button, which allows us to clear out the memory on the Dynalyzer. The switch that we will be concerned about is the printer switch. This switch has 3 positions: off, auto, which allows us to print on each and every exposure, or print, where we print out the data on the front of the display, plus the percentage of line voltage regulation and the kiloheat units per exposure. We will now move to the next slide for compatibility of Dynalyzer 2 and Dynalyzer 3 components. This slide shows the compatibility of Dynalyzer 2 components with Dynalyzer 3. Please note that the Dynalyzer 2 high voltage unit is compatible with the Dynalyzer 3 display printer and probe. The Dynalyzer 2 digital display is compatible with the Dynalyzer 3 high voltage unit and probe. The Dynalyzer 2 printer is not compatible with any units of the Dynalyzer 3, and the probe is compatible in all cases. The Dynalyzer 2 high voltage unit can be converted to Dynalyzer 3 when you send it back for its yearly calibration at Machlett. Recognizing the need for quick, accurate testing of X-ray equipment, we believe that the Dynalyzer 3 microprocessor-based X-ray calibration system is a very effective device to be used by original equipment manufacturers for debugging production equipment, final calibration, compliance testing, staging, and installation, for X-ray dealers, for installation, calibration of equipment, and servicing, for hospital personnel, for periodic calibration of equipment, servicing, and quality assurance programs. It is our intent to develop additional devices or accessories to add to the capability of this system. At the time of this presentation, October 1982, we are developing a non-invasive KVP accessory to be used with a digital display in a QA program. Please refer to the next slide. This slide shows Machlett's recommendation for a non-invasive quality assurance program. We utilize the Dynalyzer 3 digital display, the radiation probe, the quality assurance or conformance test stand, and the KVP probe, which is currently under development. Utilizing these instruments, we can obtain KVP, time, MR per second, half-value layer, focal spot location, collimator X-ray field alignment. Please note that we do not invade the circuit with the high voltage unit during this test. We'll also note that the radiation probe and the KVP probe are not used simultaneously. We are also investigating the possibility of interfacing a clamp-on current probe to the digital display for non-invasive measurement of MA. We welcome your comments or suggestions on additional tests that we can incorporate into this system. Telephone consultation or application engineering assistance in the U.S. can be obtained by calling 1-800-243-2580. International customers may obtain similar assistance by writing to Machlett Laboratories Incorporated, 1063 Hope Street, Stamford, Connecticut, 06907. Twix number 710-474-1744. Thank you for your attention.